Whether a man leads troops across open country, directs the movement of a motor convoy along a highway, navigates a steamship over the ocean, or flies an airplane through the sky, whenever a man moves from one point to another by any means at all, he must know the location of his destination with reference to his point of departure. In strictly local movements, such, for example, as routine travel about an army post, direct vision is sufficient. But as distances increase beyond the range of vision, other means must be provided. The usual method is to provide a diagram or map representing terrain features or works of man which will aid in reaching a desired destination. For extended distances, more detailed and more accurate maps are required, with the result that maps are now available for a wide variety of uses: airways maps, road maps, military maps, topographical maps, and hundreds of other special-purpose maps. Every map, regardless of its type, has certain distortions which cannot be eliminated, for the reason that maps are flat representations of curved surfaces. If the surface is peeled from a globe in wedge-shaped pieces, or gores, these distortions become readily apparent, and the extent of the resulting error is graphically illustrated by reducing these gores to a flat surface. Only at the equator are these gores in contact. Elsewhere they are separated, and the space between them indicates the degree of error of the map. While the aerial navigator knows that many methods of projection have been developed to reduce distortion, he need concern himself with only three. The first of these is known as the mnemonic projection. The mnemonic map is made by assuming a plane tangent to the Earth and then projecting terrain features upon the plane from the center of the sphere. On these maps, the meridians appear as converging straight lines, the parallels of latitude as arcs of circles. Any straight line drawn on a mnemonic map represents a true great circle, and this feature of the map explains its principal use. In plotting a course for a long flight, the points of departure and destination are joined with a straight line. Locations on this line are then identified according to their latitude and longitude for transfer to another type of map better suited to navigational purposes. Because great circles are represented as straight lines, radio bearings which travel a great circle path will appear as straight lines. However, the mnemonic projection has certain disadvantages. Boundaries and areas are very much distorted, while distances and courses are poorly represented. The Mercator projection offers a map without some of these disadvantages. In this projection, a cylinder is assumed to be tangent to the Earth at the equator. From the axis of the sphere, points on the surface of the sphere are projected onto the cylinder. Meridians are represented as equidistant straight lines. Parallels of latitude are perpendicular to the meridian. Great circle courses located on a mnemonic map can be transferred to the Mercator for actual use in navigation. The method of transfer is simple. For example, points plotted on each fifth degree of longitude on the mnemonic map are placed in similar positions on the Mercator projection. When the navigator joins the newly plotted points on the Mercator, he finds his great circle has become a curved line. Paralleling devices can be employed because true courses on the Mercator projection are represented as straight lines. Nevertheless, the Mercator map has certain disadvantages. The latitude scales expand toward the poles, and for that reason a single or uniform distance scale is worthless. A straight line between 2 points on this projection is not necessarily the shortest distance between those points on the ground. Any line representing a great circle is actually the shortest distance. A third projection is known as the Lambert conformal. It may be illustrated by placing a cone over a sphere, cutting the sphere at 2 parallels. This projection is exact only at the points where the cone cuts the sphere, but the zone considered is generally so small that errors are not great. Meridians are straight lines which meet in a common point beyond the limits of the map. Parallels are concentric circles whose centers are at the point of intersection of the meridians. Meridians and parallels intersect at right angles. A straight line is very close to being a great circle, and radio bearings approximate straight lines on this projection. One distance scale will suffice for the entire map, and areas are indicated in approximately correct proportions. But maps alone are not enough to reach a desired destination. Knowing the location of north on the map, we must know direction as well. That calls for a compass, an instrument that points to the north. Problems of navigation would be greatly simplified if the compass always pointed directly north. But it does not. Instead of pointing to the North Pole, the compass needle points to another pole, located at a considerable distance from true north, called the North Magnetic Pole. This creates an angle between the meridian and the compass needle. Being a variation from actual or true north, this angle is known as compass variation and is expressed in degrees east or west. On maps which embrace a relatively large area, variation is indicated by lines which connect points of equal variation. On maps of smaller area, one value of variation may suffice for the entire map. But every map contains this vital information in one place or another. Variation can be a very considerable factor. At Cape Cod, for example, the magnetic compass, instead of pointing north, points 15 degrees to the west, and all directions indicated by a magnetic compass in that area will be 15 degrees too high. In Northern California, a different situation prevails. The variation there is in the opposite direction and much greater, the compass pointing 20 degrees east of true north and reading 20 degrees too low. When the error is minus or easterly, the correction is obtained by addition. When the error is plus or westerly, a corrected reading is obtained by subtracting an equal number of degrees. The accuracy of the magnetic compass is affected by still another important factor: the magnetic influences in the aircraft itself. The airplane engine represents a sizable mass of magnetic material, which exerts an effect upon the magnetic compass. Structural members of steel, radio equipment and their generators, armament, and many other metallic items create a confusing magnetic pattern with corresponding compass errors. This error is known as deviation and is determined by swinging the airplane through a complete circle and checking the readings of its compass against another compass, terrain features, range markers, or known landmarks. The airplane's magnetic field can be largely neutralized by adjusting very small compensating magnets in the compass. The remaining error is recorded for every 15 degrees on a card provided for the purpose. This card is then placed near the compass for ready reference. Compass errors are likely to be present at every location, no matter where. Lines of variation cover the country and the world. Hence, a knowledge of variation and deviation contribute to ready understanding of three terms frequently encountered in problems of navigation. The first of these is true north. True north is the direction parallel to the meridian. It is the direction of north on the map, the direction in which the North Pole lies. Magnetic north is another term readily understood. Magnetic north is the direction in which a compass, unaffected by local influences, will point. It differs from true north by the variation. The third term is compass north. It is the direction in which the compass points. It differs from true north by the combined factors of variation and deviation. Expressed in other words, navigators would like the magnetic compass to point true north. However, variation causes it to point in a somewhat different direction, magnetic north. While the magnetic influences of the airplane itself, or deviation, produce another reading, compass north.